Welcome to The Explainer. Today, we're going to peek behind the curtain of our digital world and look at its invisible architecture. We are talking about the brilliant science that makes all our technology feel like pure magic: data structures and algorithms.
I mean, really think about that for a second. Your phone looks at countless roads, traffic jams, all the turns, and then bam, it spits out the perfect path almost instantly. How on earth is that even possible? Are computers just ridiculously fast? Well, yeah, but raw speed is only half the story.
The other half, and this is the really important part, is all about efficiency. It's not about just brute force, it's about working smarter, not harder. And the secret to doing that, it all starts with how you organize the information in the first place.
You know, every single app you use, every search you make, it's all dealing with a complete avalanche of data. So the real challenge for any piece of software isn't just holding all that info. It's about managing it so that it's useful, accessible, and crazy fast.
Okay, so let's get into it. To solve this huge organizational problem, computer scientists came up with these incredible blueprints for arranging data. And we call these blueprints data structures.
The key phrase on this slide is used effectively. It's all about specialization. You know, you wouldn't use a shoebox to carry water, right? It's the same idea. You wouldn't use the wrong data structure for a specific job. It's all about picking the absolute right container.
And what's so cool here is that you can really see the trade-offs. On one hand, you've got an array. It's just like that library shelf, amazing for grabbing a book in a split second if you know its exact spot, its index. But on the other hand, a linked list is way more flexible, kind of like that treasure hunt. It's perfect if you're constantly adding or removing things from the middle. So, you see, there's no single best way to do it, only the best way for what you're trying to do.
So, we've got our data organized in the right container. Great. But now what? How do we actually do stuff with it? How do we sort it or search through it? Well, that's where our second key ingredient comes into play: algorithms. Now, I know that definition sounds super technical, but don't let it fool you. An algorithm is really just a recipe. That's it. It's a very precise step-by-step list of instructions that tells the computer exactly what to do to get something done. No confusion, no guesswork.
Let's make this real. This right here is a simple sorting algorithm called insertion sort, and it works exactly the way most of us would sort a hand of playing cards. You just pick up a card and you slide it into its correct spot among the cards you're already holding. This whole process is a perfect example of that methodical, step-by-step approach that's at the heart of every single algorithm. Okay, so this brings up a really important question. We've got different data structures, we've got different algorithms. How do we actually measure them? How do we know if one recipe is genuinely better than another one?
And this is where the difference becomes just astronomical. An inefficient recipe that's totally fine for a small job can become completely, utterly useless when you try to scale it up to handle the massive amounts of data we see in the real world. We need a way to predict how it's going to behave.
And for that, we use something called Big O notation. Forget about using a stopwatch. That's going to change with every computer. Big O is like a universal language. It describes the relationship between the amount of data you're working with and how long your algorithm is going to take. It's all about the growth rate. And this table right here shows you exactly why that growth rate is everything. I mean, look at this. With 1 million items, a logarithmic algorithm is basically instant. A linear one? Totally fine. But then you get to the quadratic algorithm, and it requires 1 trillion operations. 1 trillion! That's not just slow, that's completely broken. It would never finish.
Visually, the difference is just staggering. Choosing a clever, efficient algorithm over a simple, brute force one, well, that's the difference between an app that feels instantaneous and one that would just freeze up and crash your whole system. This idea, right here, is probably the single most important concept in designing algorithms.
So this brings us right to the core of modern computer science. The whole field is basically a constant search for smarter data structures and more efficient algorithms. It's all about finding these clever ways to organize and process information that keep those growth rates down, even when the amount of data is just exploding. So, for example, take the binary search tree. It's this really smart structure where everything to the left of a point is smaller and everything to the right is larger. This lets you find something by repeatedly cutting your search area in half, which makes it incredibly fast. It's a huge step up. But there's a catch. It has a weakness. If you happen to add data that's already sorted, the tree doesn't really branch out. It just becomes this long, skinny, lopsided chain. And at that point, searching it is no better than just walking down a simple list. We've totally lost our efficiency advantage.
And this is where the innovation just keeps going. Computer scientists saw this problem and, of course, they invented a solution. And I absolutely love this description. The AVL tree, it's the smarter, younger brother of the binary search tree.
So what makes it smarter? Well, it's self-balancing. This means whenever you add or remove something, the AVL tree actually checks to see if it's getting lopsided. And if it is, it performs this clever little shuffle. It's called a rotation, to rebalance itself. It's like it has a built-in maintenance crew that keeps the whole structure perfectly efficient all the time.
And the result of all that work? You are guaranteed to get that super fast logarithmic search time, O of log n. This is the holy grail for searching. It doesn't matter what data you throw at it or what order you throw it in, it stays fast. It completely solves the weakness of its older brother.
So, let's just quickly wrap up the main ideas. Data structures are the containers, right? They're how you organize your info. Algorithms are the recipes that act on that info. And efficiency, or big O, is the scorecard that tells us if our solution can actually work at scale. These three things all work together.
At the end of the day, this isn't just some abstract theory. This is the fundamental engineering that makes our entire modern world possible. From your GPS to your social media feed to the entire global financial system, it all runs on this invisible foundation of clever data organization and lightning-fast recipes. And that kind of leaves us with a final thought. We are creating data at a pace humanity has never, ever seen before. The challenges of tomorrow are going to require even smarter containers and even faster recipes. The hunt for efficiency, it's never really over. So what comes next?